In addition to demographics, there are specific age distributions for a group, and that depends not only on the organism itself, but on the conditions the organism is living in. For this, please be able to describe age distribution, fecundity, generation time, the geometric rate of increase, R naught, lambda, T, and R. The book does a very good job of going through those last four things, so it would be wise to review that. Using Excel, calculate growth rates given demographic information, and that's an in-class activity. Relate age distributions to population growth, define fecundity by life stage, calculated generation time. The book does a great job. I think it uses turtles. And use the equation for the geometric rate of increase. So, age class structures. Here we have a population that shows trees in an undisturbed forest. A lot of them are 10 years old, and fewer of them get older and older. It's the opposite of what we have in our forest. But in an overgrazed forest, it turns out that there's mostly 40 or 50-year-old trees. The younger trees cannot survive because the deer are grazing them to death. So you see, one species here has two different age class structures. Now, you may think of semoparous organisms as having, type 3 organisms, which are often semoparous, having lots and lots of young and very few old ones, but the young aren't going to survive the year. That could be their age class structure, but it really depends on what's going on. So predation, parasitism, disease, herbivory, and the conditions of the environment all affect the age class structure. Here are three examples from 2011, I believe, and an NPR article from 2018, actually, with the U.S. birth rate. Afghanistan has a lot of young people, or had during this time of the picture. The United States has relatively, so this means a lot of people are entering the most fecund years of their lives, which would be ages about 19 through 35. And in the United States, there aren't very many people in that compared to everywhere else, but there are enough to maintain growth. Whereas in Italy, there are not very many people in that age 19 to 35. An interesting fact in this year 2020, which tragic though it may be, is that in Italy, that graph got moved forward about 9 years, placing most people on the other side of the 40-year-old divide, which is one reason the coronavirus was so deadly there, was due to their very different age class structure. So this is actually affected by birth rate, it's affected by industrialization. It's actually, as a nation industrializes, there's generally an increase in lifespan and a decrease in fecundity. So the age-specific fecundity actually goes down, and the percent of the population that is around 0 to 4 to 5 to 9 goes down as well. Pretty much since Prince died in 2016, the U.S. birth rate has just been falling and falling. That's what it sounds like when doves cry, man. Anyway, so it's affected a lot by reproductive strategies. Again, semoparity or iteroparity will affect the age class structure, and you can imagine that the survivorship curve also affects the age class structure, because if most organisms survive to an old age, then you're going to have a lot of old organisms. So that just makes a lot of sense. All right, now some more complex stuff. Fecundity. Okay. Fecundity is how much offspring can be reproduced. And I want to remember the n, then the n sub x is the number surviving to unit x. The L sub x is the proportion surviving to unit x. The m sub x is the average number of offspring for each individual during that time interval, x. If you multiply L sub x and n sub x, L and m sub x, you're going to get the age-specific fecundity. If you sum all those age-specific fecundity, it's going to yield something known as R0. So let's go back just a step. M sub x. So this shows that this Phlox drumundii, which is a type of plant, don't know why they have eggs there, but basically it's got how many seeds? Most of its seeds are going to be produced between 313 and 327 day. No, actually it keeps going. Then 341 days. So it has a certain age-specific fecundity where most of the seeds are produced. And the proportion that's surviving till that are going to be the ones that are actually producing and leaving seeds. So how many offspring does each individual leave is female specific, though phlox is male and female being a plant. That's your M sub x. And then your R sub naught is your net reproductive rate per individual, calculated by the sum of all the LX, MX. That's the net reproductive rate per individual. Per capita rate of increase is a little something else, but the net reproduction rate. If it's greater than 1, it indicates the population is growing. If it's less than 1, like it was in the beavers in a different lecture, it indicates the population is shrinking. This is very similar to the virus thing. If it's spreading, it means that the spread rate is greater than 1. And if it's decreasing, then it means the spread rate is lower than 1. So let's say that wearing a mask, if the whole population wore a mask, you could turn the virus's spread rate from 1.1 to 0.9. Well, that would actually decrease the virus rate and it would eventually go extinct. If that was all it took to decrease the virus rate, and it just moved it on the other side of 1, well, then that's enough. It takes a long time. But if it changed it from, say, 2 to 0.25, well, then the virus is going to go extinct in basically a few generations. Not bad at all. It's that or it expands. So you can compare M sub x to a term you may be hearing, which is your R. So you compare R to what you may hear from viruses, which is also R. Okay. Another thing we can look at is the geometric rate of increase, and that's lambda. And lambda, I'm just going to write it as an L down there, is equal to n at t minus plus 1 over nt. If lambda is greater than 1, it means this population is bigger than this population. If lambda is less than 1, it means this is less than this. It's a fraction thing. It's improper fraction or non-improper fraction. So we're looking at your geometric rate of increase here for cockroaches. If each cockroach makes 10 new cockroaches, that is your net reproductive rate per individual. Then in 3 months, you have more, and each one makes 10, each one makes 10. It's a pyramid scheme, really, if you drew it out like, you draw it out, each one makes 2, each one makes 2. It's going to be a bit of a pyramid scheme. If you were to measure the number along that side, though, it's going to double every population, or this time it's going to be times 10 every population, assuming the first ones aren't dying off. And that's called the geometric rate of increase, is when you're increasing at that kind of constant rate per unit. So geometric rate of increase, remember, is a per unit rate of increase. So you're measuring it at this month, the next month, the next month. This really works well for things like plants, which are going to have a geometric rate of increase because they're seasonal. So they're going to grow up, set seed, and that's going to be a geometric rate of increase measured by the population expanding at a constant rate. And the constant rate often leads to a vast and fast expansion. But obviously that can't continue forever. All right. This is what we're doing in class. There's probably a way we can do this online. Everything will be provided online. Everything's on Moodle, so you can pretty much just follow through the directions. It's just going to be harder to ask me questions. Come to Zoom office hours if you really need help. We'll work on this, but I'm going to skip right through this because some of you came here for review. So generation time. So the generation time is the sum of x, Lx, Mx, divided by R naught. So you might just see, well, the sum of Lx, Mx is R naught. So it's the sum of the x, though. You're adding how many years there are into this summation equation. So you're multiplying these 3 columns for every single time. So you can get that generation time t. That's how you're going to get t, is the x, sum of x, Lx, Mx divided by your R naught. And if you were to take the natural log of R naught and divide it by generation time, that's how you get what's called R, which is the per capita rate of increase. So how fast is it increasing? You have a unit of time and you have individuals. So how many individuals per unit time? And this comes in handy for just about everything else we're going to be doing for the next couple of lectures. So, yeah. Generation time is not the age of individuals when they die. It's the average age when they reproduce. Remember, some individuals are interoperous and they reproduce multiple times too. So for semoparous individuals, generation time is the age of individuals at death, which you'll be able to find out by adding the x sub x lx mx for a semoparous individual. Mx is 0 for almost all of its life. So it's just the that last x lx is going to be all that really matters there for a semoparous individual. So most of these are interoparous. We'll be using this more. Interestingly, I'm going to stop making lectures for a little while. You don't know when I'm making this right now, but this is about halfway through the semester. So I'm stopping these lectures until I can get some feedback on how the lectures actually were. So you'll actually notice this kind of pause, and then if there are changes students suggest, there might be changes moving forward, or I might have deleted this one and changed it. Interesting to think.